So we left off with bar graphs, bar plots, tables. There we go. Make sure this works. Yeah, so we finish this up. I have a homework assignment that will make go live, so it gives you practice doing some of these things. Again, just kind of reinforces reading in data and everything. So we finished up with bar graphs, histograms. So bar graphs are all about count data, frequency data. We have separation between the bars to emphasize you could say the discrete nature, or discrete is the appropriate term. It's more of like the categorical nature of the data, of the underlying data. When we have continuous data, we don't really want to emphasize the separations. We don't want to emphasize the groups. All right, our figures should reflect the fact that our data are, continuous in some nature, and this is what histograms do. All right, so the histograms are frequencies. They show your counts, or they'll show percentages of the total. And they look superficially similar to a bar plot, but you can see that we have each of our bars touches. So it emphasizes that our values just kind of go together. They're continuous, all right? So how do we do it? Well, hist. That's our function. And we're going to learn variation on this function. But this is a histogram of our quantitative data, so plant counts in our grids. If you read in the data and you call it quant data, so like just what we had in our R Studio. So if I open mine up, it's over. Right. So open this up. I already have my chunk that reads in the data. All right. What happened here? Again. Oh no. The environment is empty. Worked. Should be there. The environment's empty. So let me go ahead and close it out. Reopen it. Let's fix it. And now let's try it. There it is. Quant data. All right. So we did our box, bar plot. This will be figures, quantitative data, histograms, express frequencies. Function is hist and our vector. And then there's some additional options. All right, but we have to pass it a vector, and our vector is a numeric vector. All right, so vector is a numeric vector. If you try to pass it like a vector of names, vector of texts, you'll get an error, and it just won't do it. So we need a numeric vector in order to get it. So our example here is the hist quant data and plants. When I run that, we can see that we get our histogram that is produced. And just like with all of our other figures, we can edit it, we can modify it, change the labels, change the titles. We can even change the font types if we want. And there's a lot of different things that we could do to edit these figures if you choose to do that. But again, we could have an entire class just on figures. And I'm not saying like a one class a day talk. I'd say like a 3-hour course on making figures in R. So if you need to make it look nice for publication, come talk to me. I'll help you out. All right. So making frequency distributions. All right. So we're going to go into a little bit more detail on these histograms. So this just summarizes. So we're trying to add up frequencies. We're trying to report frequencies. If we have qualitative data, hopefully it's self-explanatory. You figure out what groups you have, and you just count how many items there are in each group. Discrete data, same thing. We've got our counts. If we record how many males are in a clutch, and we've got 100 different clutches, it's pretty easy just to kind of sum up and say, okay, we had 5 clutches that had 0 males, and we had 10 clutches that had 1 male, and so forth. All right. If they're really large, let's say our clutch size could be 50. All right, we probably need to combine the groups so that we don't have 50 rows in our table. But again, it just kind of depends on the data. If we have quantitative data, then the recommendation is always to use the stats program. Try to avoid doing stuff by hand. And the reason is that R will automatically look at your data and assign the groups. And it'll assign the groups as best it can to make the figure look pretty. All right. So when it forms these groups are called bins. R will make it based on our data, but we might need it to have more bars. We may need less bins and so forth. So typically, what we strive for is 12 to 20. That should give us enough detail in the data to judge how good our curve looks like for a bell curve, but not so much that we don't see any trends in the data. So we can control this. If we can let R do everything we want by just using the hist and our vector, but let's say we want to increase the number of bars that we have, we use breaks. That's what breaks is for. And again, R will try to do things, make the graph look pretty. So don't think that if you do breaks equals 5 and then breaks equals 6, that you'll see a change. A lot of times R will say, yeah, you know what? You want me to increase it by 1? It doesn't look pretty, so I won't do it. So sometimes we have to really increase it. So here's an example, just to kind of demonstrate the use of breaks. This code, it generates a random distribution of data, draws 1,000 data points. All right. So I'm going to move over here and just kind of add on. So we're doing demonstration of breaks. We will first create a random vector of 1,000 data points drawn from a normal distribution. All right. So I'm going to call it X. All right. And when I run this, you're going to see that we get a vector, a numeric vector. Now, you don't have to know what the normal distribution 0, 1 means. We'll talk about this because, again, it's one of our main assumptions for our statistical tests, that we're normally distributed, and we'll learn how to test that assumption. But what we're doing is I have 1,000 data points here drawn from this normal distribution, and I'm going to save it as vector X. Now, with our vector, we're going to make a histogram. So we're going to let R make the histogram that it thinks is going to look best. And when we do it, yeah, I look at this and say, yeah, this is actually pretty decent. All right, this is a pretty decent curve. All right, I've got, if you think of a normal bell curve, this kind of looks like a normal bell curve. All right, we might have a point that's, this bar might be up a little too high, maybe. Or maybe this bar is down a little too low. All right, so we can look at this and say, maybe we want more bars. All right, so how do we do that? Well, we use the breaks. Okay, so maybe we want more bars in the histogram. Let's use the breaks option. Let's use the breaks equals n option. So we'll do, in our hist function, we'll use hist x, and then I have a comma, and now we're specifying options that get passed to the histogram function. So I'm going to do breaks equals, and n is going to be our number. So let's say we want 100 bars. All right, so we've got 1,000 data points. If I use breaks equal 100, we're getting about 100 bars. So each bar should have, in theory, about 10. We'll run it and see what it looks like. And that's what we get. So you can see how we've added. The breaks doesn't say how many bars, it's how many breakpoints do we have in our data set. That's really what it's doing. But again, R tries to find pretty breaks. Pretty breakpoints. So at 100, that looks, yeah, it's probably suitable. I don't like it. I think there's way too many bars here. You see all of these peaks and valleys. Our bell curve should have most of the points in the middle, and you see we've got high value, low value, and it's all jumbled up. We might look at this and say, you know what, there's too much information here. We don't need that. We don't need all of this information. So let's reduce the number of bars. So let's say we want fewer bars. So same thing, I'm going to use hist x, and I'm going to specify breaks equals 5. Just to kind of do an extreme. I thought 5 did an extreme. See, now everyth's kind of washed out. Groups are put together. We don't see a huge amount of detail. I mean, the bar goes between 0 and -1, and this one from 0 to 1. That's a huge number of data points. I mean, are there really, what's going on? Do we really jump from here to here all the way up? Is it a smooth curve? And so forth. If I put it down even lower, you can see now, I do 3 breaks, that's even worse. I mean, there is no detail. I couldn't judge if this was a normal curve or not. 6. See, 5 and 6 doesn't look like they changed at all. 5 or 6, so let's go up to 10. 10's a little bit better instead. I think 10's is what R did. R used. Yep.
My break equals 5 is like this.
Maybe let me resize it. Rerun.
This thing was like, yeah, 3, right?
Try it out to 6.
No, I went 6.
Oh yeah, there it is. See? I don't know. Stupid computer. Stupid computer. No, I mean no big deal. We're just demonstrating how we can use the breaks. We will be using the breaks. I'd say, when we oops, here, as we start looking at making more and more histograms, you'll have a better feel. Normally, again, R does a good job at making the histogram, but sometimes we want a little bit more control. We want to see a little bit more detail. So, all right. That's it. All right, so there is a way to make things by hand. There is a way to make things by hand. And what you have to do is kind of arrange your data in order from lowest value to largest value. And then you have to figure out where your breaks are. And then once you figure out where your breaks are, then you start counting your data points in each of those breaks. All right? As part of this decision, you have to decide how are we going to label those breaks. Are we going to use the midpoint of the values? Are we going to just label the left or the right? How do you include value? What do you do if our break is at 1? So if the value is 1, are you included in that one, or are you included in the next one, and all this stuff? A lot of decisions, but once you have that, then you basically go ahead and construct the histogram at that point. That's what you have to do in Excel. You have to go through and generate the bins yourself. Now there are a couple, the data analysis package, I believe, has an option to generate these bins for you, but it's still time consuming. Better way, just go ahead and do this. Get these data, make a vector. You have these data, and it's like, okay, I want to make a histogram. How hard will it be to add these data to R as a vector and then make a histogram? Not hard at all, right? So go ahead and do it, just to demonstrate the ease of making a histogram in R. And this is probably the way that I would do. So I'll leave this up. So I arrange these numbers from smallest to largest just to make it easier on us. So if you succeeded, you'll probably have a histogram that looks something like this. Made my vector. I called it EX1. Call it whatever you want. Made my object, used the hist function, and we get a histogram like this. Pretty easy. All right. Now, there could be times when you really want to make a histogram, but you don't have a computer handy, or you don't have a computer with R handy, could we actually make a histogram by hand? Yes, but there's this other figure type that would relay a lot of the same information as a histogram. And it's way easier to do by hand. And that is a stem and leaf display. All right, so R can do this. We'll demonstrate it as well. All right, but R can do this. So how do we do our stem and leaf display? The stem and leaf is simply an ordered array. That's basically what a histogram is as well. But stem and leaf display is an ordered array. It's super easy to make by hand because all that we're going to do is first make our stem, which are the leading digits, and then we're going to add the leaves, which are the last digit in our number. And what we're basically doing is our stems are our groups, those are our bins, and then how many values we have, how many leaves after that relays that frequency count, or the frequency, the counts of that. So I'm going to leave this up here, and I'm going to move over to that board, show you how I can make a stem and leaf display just by hand. And again, how often would you use this? Depends on what type of data. I have used it out in the field. I didn't have my computer, and I was just curious what the underlying data looked like. So we're going to make an ordered array. So I've got my stem. These will be the leaves. So I look at all of my data points. The smallest number that I had is 6.3. The largest is 11. So my stem are 6, 7, 8, 9, 10, 11. Smallest to largest. Our leaves are those decimal places. So I'm just going to go right down my columns and add the leaves. So 8.7, that's one leaf. 8.5, second leaf. 9.4, and I'm going to try to line them up vertically. 10.0, 6.3, 7.8, 11.9, 6.5, 6.6, 7.6. So if I line them up correctly, then we can kind of judge judge frequencies based on how long this is, how long those leads are. Now we're not done, so the next step then is to order these from smallest to largest. Switch those. Switch this. Now we have an ordered array. And if you can think about a histogram, if I take this and just flip it on its side, since I maintain columns, these columns are basically bars. These would represent our histogram. So you can kind of very quickly make something like this to get a judge for, to have this nice bell-shaped curve, or is it something more flat like this? Pretty easy. right? R can also do this, right, using stem. So what I will ask, I do have the next slide gives you A and B, where you share the stem and go side by side. But what I'm going to ask is to go back to this vector. It's already ordered for you, and make a stem and leaf display just by hand, on a piece of paper, just so you can see how this stem and leaf looks very similar to a histogram. I will do is this one up on the board. So, looks similar to our histogram, right? We could combine groups if we wanted to. We could expand groups if we wanted to. Just all done by hand. It avoids having to kind of figure out where our groups are. We just let the data use whole numbers, or if we've got 3 decimal places, we use that last decimal place as our leaf, and everything else before that as our stems. How do we do it in R? It's stem. That's the function. So, all right, so stem, vector, scale. Scale expands or contracts the group. All right. So EX1, right? That's our histogram, or the histogram that I have. Back here. This is our histogram for the EX1 vector. So I will use stem EX1. All right, and you can see the scale is already set to 1. So I'm going to use scale equals 1, because that's the default. And you can see that that is the exact same stem and leaf diagram that we just did by hand. Let's change scale. What kind of values do you think the scale will take? First up, let's check the help file. Oops. Help file. Oops. Stem. There we go. Stem and leaf plots. Scale controls the plot length. The length is this. How many stems do we actually have? All right. So that's all it says. But in the description, a value of scale equals 2 will cause the plot to be roughly twice as long as the default. So if that's our default, if I change it to scale 2, look what it does. It makes it twice as long, which basically says we're going to make our breaks at 0.5. I don't think we had any of the 0.5s on there. But now you've got 2 of these stems. And it would be up to you to recognize that we're going basically 0, 1, 2, 3, 4, and then 5, 6, 7, 8, and 9 would be our 2 groups. So if we did it 3, scale is 3, that makes it 3 times as long. But it didn't. Let's see, let's try to do 4. So we're capped. Oh, no, 5 works. Now you can see when we did 5, it split apart. It tells us the decimal point is 1 digit to the left of this. So it's 2.00, 2.20, 2.40, and so forth. So we can expand it, contract it how we see fit. What if we use 0.5? So half the scale, we compress it. So there might be a time where we make a histogram or we do something like this by hand, and then we check our work with R, but R, might do something like this because we have so many numbers. You say, okay, well, that's not right. Well, just remember, we can use a scale to change, how long that stem actually is. All right, so nice thing about the stem and leaf diagrams when we do it by hand is that we could do it back to back. So we could have a stem that is shared, and then we've got group A going to the left, group B going to the right, and then we could kind of judge our histograms, our central location and tendency and stuff. So I had this up here just to kind of demonstrate how we would do it, but reality is we typically don't. All right, so if you want to work through this, if you want to try to make it yourself, make a side-by-side graph, you can, and then we can check our work in lab if you want. But I'm not going to make you do this. All right? Questions? All right. So I do have a homework assignment. I believe it's already posted. Let me make it available. What's that? I did. No, that should be homework 1. Yep. All right. Make it. There we go. Homework 2, data in biology. So I typically put the keys outside my office. Have them as a PDF. Shows you, how I do stuff. I'm just, instead of, if there's a chance that you're in quarantine or isolation and can't get up here, I'm just going to go ahead and get the keys posted on Blackboard so that way you can still access it from at home. But data in biology, I've got 2 data files. The RMD file that you could open up. And this one is, you'll see, is surrounding, doing a table, and you can just type in your answers, because then when you knit it, this R will automatically make this a nice table in Looker. Even if I do something like this, things aren't lined up, that's fine. What R is looking for are these pipe symbols to know when my columns work. So you've got rounding on here, making a vector, doing a histogram, butterfat. Again, just more practice with R. You can work on it this afternoon once we finish the lecture portion of the lab. If you want to do it, work on it at home, you can. I didn't set a due date yet, so let's go ahead and set a due date. We'll do Wednesday. We'll do it like Wednesday at like 5 or whatever. So that way, if you're doing it, if you run into trouble or if you have problems knitting, you can bring those questions to class on Wednesday. We can answer it, and then you have time later that day to fix it or do whatever to get it up. All right. Let's move on. So this has all been providing background information to get to this point, which is to actually get into calculating the numbers, doing summary statistics, doing inferential statistics, knowing frequencies, or knowing variable types and scales. Yeah, types, super important, because that tells us what tests are available to us. Scale, not so much. So what we're going to do is cover descriptive statistics. I don't think I'm going to have, I don't remember, but I don't think we're going to do a lot of these calculations by hand. We're going to use a computer. I can show you how to use your calculators to enter in a data set and then have the calculator calculate means and variances. But for the most part, we're going to learn, you're going to see the equations, and then we're going to, yeah, what's that? Oh yeah. We're going to see the equations, and I might show you how to do it. I need a few times, but all right. We'll get this cleaned up. All right, so this was chapter 2 in that OpenStax textbook. All right, so how do we describe our data? We describe our data using 2 measures. There are 2 metrics. Anytime we report data, we're always doing 2 different things. We are reporting some measure of central tendency or some measure of location. All right, where are we at on our axis? All right, and then we're also reporting some measure of variability or dispersion of our data. Okay, we're going to try to show how much variation we have. Our options for both of these vary based on how we're going to analyze our data and what we use it for. All right, so what we're going to do for this presentation is I'm going to introduce you to some of the random number generators. All right, so we can work through some just random samples. And if you ever need to do a random vector, you know how to do it. All right, so these random number generators aren't truly random. They are computer generated, so the computer is going to use some sort of formula to generate each item in our list. That can be useful because we can set a starting point for that random number generator, and that ensures that every time we run that random number generator, we get a repeatable pattern. We get the same numbers. All right. So how do we do it in R? We do it with the set.seed function. So it's going to set the seed, set the starting point of a random number generator, and then every time we run that, as long as we set the seed at the beginning, we're always going to get the same exact number. All right. So let's do that. I'm getting my R markdown document. Save this. All right. So we're going to generate the data first. Oops. And what we are going to do set.seed sets the starting point for the random number generator. It's going to be good for us in this class so that when I do make a random vector, you get the exact same random vector as I do. All right? If we didn't do this, then the first time we run a random number generator, R will look at the system time, so like milliseconds or microseconds, and say that number is going to be our starting point. So no matter how hard we try to hit enter at the exact same time, there's going to be a slight difference. It's highly unlikely that we would get it at the exact same time. But the setC function accomplishes the same thing. So let's go ahead and do set.seed. Pick a number. 12. There you go. We're going to set the seed at 12. All right? All right. So what I will do we're going to round this just to demonstrate it. 1, actually, 0, max is 10. All right. So just to demonstrate, we're going to create 10 random numbers. All right. Those are my random numbers. And if I run this over and over again, I'll keep getting a different set. Okay? So I just keep getting a different set. If I go back and set the seed at set.seed 12 and run it, these are the numbers I get. So now you go back, you run the set seed, and you run this function and see if you get the exact same numbers in that order. Now, if I run it a second time, I'm going to get a different batch, but we set the starting point. So the starting point found this number, 1. Then it moved to this number and this number and this number. So it's a predefined pattern if we knew where we were starting. All right? Hopefully you see this, right? So we're going to set the seed to establish a fixed pattern of numbers that everyone has the exact same vector. That we're going to, everyone has the exact same vector for this presentation. All right, the distributions that we're going to use is the normal distribution, Poisson distribution, and the exponential distribution. I used, on this, the uniform distribution. So every number had the same probability of being drawn. Number between 0 and 10, this actually goes to, I don't know, 10 decimal places, 16 decimal places. I rounded it just so we can get whole numbers. All right, but this was a uniform distribution is what I used here. These distributions, to generate the random number, uses R at the front. So this basically says generate a random number, R, from the normal distribution. All right, this is a random number from the Poisson distribution, a random number from the exponential distribution. Well, as you'll see, these distributions are defined by a certain value. All right, for the normal distribution, it's defined by the mean and the standard deviation. So we have an infinite number of curves from the normal distribution. Poisson distribution is defined by lambda, which is the average. Poisson is also a discrete distribution. The exponential is defined by a rate. All right, what is the n? The n tells us how many samples we actually are drawing from that distribution. All right? So we set the seed at 12, and we use this round and run it to get it. So now what we're going to do, I say run these in R. All All right, so I'm gonna move this over here so you can see it. First thing we're gonna do, I have this chunk, and at the very start of that chunk, I'm gonna set the seed at 2015. And I did that because it's all our figures and stuff and averages match to these. And then I'm gonna have AV1, AV2, and AV3. So basically average 1, average 2, average 3. We'll use these to kind of calculate means and variances and so forth. Then I'm gonna move this out of the way so that I can copy these codes. So go ahead and do that, and then I'll kind of talk you through what each line is doing. Oops. I guess we're using the chi-square instead of the exponential. So you can catch that. Oops. So I've got my code in R, all right? And I'm just gonna run the chunk just to confirm that they ran. They did. And I'm going to make sure I save it because we are out of time. What we'll do is we'll pick this up. So if you didn't quite finish getting it into a chunk, get this code into a chunk. And we need that set.seed in that chunk, so when we run the chunk, we're going to get the exact same numbers. So my AV1 is the same as your AV1. AV2, all the same across class. And what we'll do is we'll pick up, review this, and I'll go line by line and tell you what each thing is doing. All right? All right. Yep. Okay. Save, close, and then reopen. Because that's what worked for me.